When a major infrastructure project fails, the cause is rarely a shortage of concrete or steel. It is a shortage of accurate information. Data fragmentation remains the primary bottleneck in heavy civil construction. For decades, the industry relied on 2D CAD, a workflow of isolated drawings and static notes that allowed critical data to vanish every time plans changed hands. Building information modeling is often mistaken for a high-fidelity version of those same traditional drafting methods. In practice, BIM functions as a relational database. It treats 3D geometry as just one of many queryable outputs generated from an interconnected web of engineering data. For highways and bridges, this specialized application is known as BRIM, Bridge Information Modeling, engineered to handle the unique variables of linear infrastructure. Understanding this shift requires building a 5D federated model from the ground up, a process that begins months before the first beam arrives on site. Adopting this workflow establishes a digital ecosystem that identifies and neutralizes project risks before they ever reach the physical site. Unlike vertical construction, linear infrastructure must span diverse topographies, shifting soil types, and sensitive environmental zones. Because of these variables, the digital workflow starts with raw spatial data collection long before geometric design begins. Survey teams aggregate millions of measurements from LiDAR and drones to generate a high-fidelity topographical mesh. Engineers map geotechnical data into this mesh, identifying subterranean bedrock and soil strata. Planners then test 3D alignments, snapping highway geometry to these exact topographical constraints. Within this data-rich environment, traffic simulations and environmental impacts are measured directly against the proposed route. Locking in these real-world constraints digitally allows teams to eliminate the foundational uncertainties that lead to project delays. As the terrain is finalized, the focus shifts to the structure. A complex bridge requires independent designs from structural, geotechnical, and electrical specialists. These specialized files merge into a federated model, a single digital environment where every architectural, structural, and mechanical system resides. The BIM engineer verifies data consistency across these merged disciplines, enforcing structural logic within the combined model. This centralization enables the most powerful tool in preemptive coordination, automated clash detection. If a structural load-bearing footing intersects with a planned drainage network, the software flags the geometric overlap, pulsing bright red to indicate a hard clash. Resolving the conflict in the digital space allows for a rerouted drainage path before any physical components are manufactured. In modern infrastructure contracts, this automated checking typically results in a 30 to 40% reduction in field requests for information. Clash detection shifts problem-solving from the expensive physical worksite to the low-risk digital environment. Even a clash-free 3D model is ineffective if the construction sequence cannot be executed on the ground. This introduces the fourth dimension of BIM, time sequencing. Every 3D component is hyperlinked to a chronological project schedule, creating a visual timeline of the entire build. Contractors use 4D sequencing to simulate crane logistics and stage deck installations, uncovering resource conflicts before they stall the site. This logistical pre-planning leads to schedule compressions of 8 to 12% on repeated infrastructure types. The model then adds the fifth dimension, cost integration. Because the system is a database, it automatically calculates the volume of materials required based on the geometry, a process known as quantity takeoff. If the bridge span is lengthened, the database updates material quantities and the project's financial baseline in real time. 4D and 5D integration converts a static design into a predictive engine for logistics and finance. As a project moves toward groundbreaking, the informational density of the model must increase. This density is measured by the level of development, or LOD scale. It begins with conceptual massing at LOD 100 and culminates in exact fabrication precision at LOD 400. At LOD 400, every physical element contains specific bolt placements, structural material grades, and detailed manufacturer warranty data. Cloud platforms deliver this high-fidelity data directly to tablets and mobile devices used by field workers on site. Providing LOD 400 data to the field bridges the gap between the design office and the construction site, ensuring the physical build matches the engineering. A BIM model's utility continues long after construction is complete and the asset is handed over to the owner. In modern infrastructure, the as-built model transitions into a digital twin. A digital twin acts as a dynamic tool for long-term operations and maintenance. Sensors on the physical bridge stream live telemetry directly into the digital twin database, tracking structural vibration patterns, environmental wear, and stress from traffic loads. This structural health monitoring allows authorities to move from reactive repairs toward efficient, predictive maintenance. Building information modeling integrates concrete assets with live telemetry, resulting in a continuously monitored digital system.